maybe we can start. Maybe just let me say, well, thank you very much for coming back to the session in spite of the rescheduling. Of course, it's been a bit troublesome with the Zoom on Monday, but I'm very grateful to see all of you there. For those of you that don't know me personally, my name is Longo, and I'm based at the Technical University of Munich. Today I will be talking about monotone skew-product semiflows for Carathéodory delay differential equations. And this is a presentation that stems from a work that we did with Rafael Obaya and Silvia Novo from the University of Valladolid in Spain. So we've been producing a few work on Carathéodory delay differential equations since I was a PhD student under Rafael and Silvia's supervision. And this is just our last production in this sense. So let me start basically by introducing what a Carathéodory delay differential Carathéodory equation is. And I will specifically do it from presenting an ordinary differential problem, okay? So we're just dealing with the differential equation in which our vector field is Borel measurable in the product space. And for every compact set K in the N, there's a function Mk that is locally integrable, and that it's a bound for the modulus of F almost everywhere on T for every X in K. So of course, Mk depends on the compact set, and there's a whole family depending on K. The family of these functions are called M bounds for F, and they have a strategic role in the theory. First of all, of course, they guarantee that this problem makes sense because the equivalent integral problem makes sense. But as we will see, I will say something more in the next slides. They have also an important, a crucial importance for the dynamic results. So specifically, we also consider a Lipschitz condition. So we will call this function Lipschitz Carathéodory. And that means that for every compact set K, we also have another function Lk, locally integrable, such that for almost every T in R, this is a Lipschitz coefficient for the function F, anytime X and Y are in the compact. So again, we have a family of functions like that, and we call them L bounds for the function F. So as you can see, it's a very mild set of assumption on the regularity of F. F is continuous in X for almost every T, but possibly discontinuous in T, and not necessarily bounded. Of course, anything that is continuous and bounded and smooth and nice is also Carathéodory, okay? So what's the reason why we studied this problem? Well, probably I think that the main interest for us is to continue this theory, dynamic theory, introduced by Sell in the 60s and then developed again further by Arstein in the 70s. Specifically because we believe that it sits very well in between these two main branches of non-autonomous dynamical systems, the smooth deterministic ones and the random. As a matter of fact, with Carathéodory differential equation, we still have a strong topological structure, but of course we lose a lot of regularity, and we're just dealing mostly with a measurable vector field. Of course, Carathéodory differential equations were introduced at the beginning of the 20th century, and the reason they are important is because they are applied in plenty of fields of science and engineering. So for example, in control theory, whenever you have switches, but also in ecology or mechanics, where they study resilience of the system and so on and so forth. So in any case in which you don't have a continuous unbounded, bounded or uniformly continuous setting, these sort of equations can be of use. Okay. The way we approach the question and the way we study the dynamical system induced by this equation is by looking at the associated skew-product flow. So I'm going to say a few words about the general technique. So when you have a non-autonomous system, you cannot construct a flow by using just the solution of the differential equation. you have to keep track of the evolution of the vector field in time, where this GT is defined as you can see in this formula. It's just the time translation at time t plus s. The reason for that is that otherwise you don't have the group structure. So if you look at this picture, if you want to see what's the value of the function, the solution at time t plus s, then you can do it in 2 steps. But if you want to see the solution as the solution at time t with initial data, what you got at time s, well, you should keep in mind that, of course, your vector field has changed. So you cannot use G as your vector field, but you have to use GS. So that's why you have to keep track of them. And we call this flow that we can retrieve skew product, because the first component is independent on the second, but affects the second. So clearly, we're not dealing anymore just with one differential equation, but with a whole family of differential equations whose vector fields are the time translation of the original one, and also possible limits. So this is actually the crucial point, because you want this function, this flow to be continuous, so that, you know, when you have a continuous flow, then you have a variety of techniques from dynamical systems that you can use to understand the long-term behavior, attractors, and so on and so forth. But to do so, you have to keep to look carefully at what's the structure, the topological structure behind this function, so that you make the closure and take limits in the right topology. So in the classic setting, when you have a continuous function bounded, then you use the compact open topology. But clearly in this case, when you don't have a function that's even continuous necessarily, then it doesn't make sense. Okay, let me say that we will make, so we call this closure of the time translation the hull of the function f. Okay, so as regards Carathéodory differential equations, the first results are in the 60s. Opel studied linear problems, and he introduced some topologies of integral type. Who went really a little bit more in the depth of the problem were Sell and Miller, that introduced several topologies of continuity for these kind of equations. And then again, Arstein, that in the 70s studied very in depth the problem of weak topologies, and also problem of compactness of the flow. So what we did in the past years, starting 2016, we picked up this theory that was mostly abandoned, and we filled the gaps, because so that the theory that we developed could relate all these results. And specifically, one important thing is that we introduce optimal metric topology, guaranteeing the continuity of the skew-product flow, so that it's clear that you cannot avoid any of the assumptions that are in these papers if you want to obtain the most useful case. So in all these results, there's a couple of definitions, a couple of properties which are crucial. We call them L1 lock equicontinuity of the M bounds and L1 lock boundedness of the L bounds. Remember, I introduced this family of functions in the first slides. They're the ones that are the bound for the modulus of f and the Lipschitz coefficients for f. So basically, they are nothing more than the equicontinuity and the boundedness in integral sense in L1 lock. The importance of these properties is that when you have one of them or both, they convey some sort of uniformity on the behavior of the solutions or the relative differential equation. So specifically, let me say, at least as regards bounded L bounds, one of the crucial results in our theory is that with this property, you obtain equivalence of many topologies. I'm being a little bit sloppy here, but I'll be a little bit clearer later. And specifically, equivalence of many topologies, among which there are the ones that make the flow continuous. And even though they are possibly difficult to be spotted in the beginning. So fortunately, they are all equivalent, and they are equivalent also to some very handleable topologies that just require some pointwise convergence. Anyways, so let me go back now to the delay differential problem. We are basically in the same setting, but now your differential problem depends not just on the current state, but also on the state in the past with a delay, constant delay. But we are applying still Lipschitz-Carathéodory conditions, of course, now in R2N. Well, now, if you want to construct a semiflow starting from there, of course, there's a substantial difference because our extended phase space now is the hull of F times the continuous function from -1, 0 to Rn. Well, this is clear because, of course, the initial datum for this equation cannot be a point in Rn. It must be a function defined on -1, 0. So, of course, if you want to construct a flow, you have to consider this extended phase space, which makes the problem substantially different because now you're dealing with an infinite differential problem. This has a huge impact on the topological structure of the theory in some sense. For simplicity, I'm going to reduce this notation just to capital C for the next slides. So what we did at the beginning was to extend, of course, with the proper differences, the theory with the M bounds and the L bounds also to the theory, to equations, delay differential equations with constant delay. This is what you can see in this reference. But of course, then one asks what happens and what can be done when you don't have these properties, or it's difficult to prove that they apply to your problem. Well, if you look into the theory, it seems already clear that it's in general difficult, or it's practically impossible to obtain any global continuity of this skew-product semiflow. Nevertheless, there's a class of equation, which is the one that are called monotone, induce a monotone skew-product semiflow, for which it's actually possible to retrieve the continuity and obtain information on the long-term behavior of the solutions. So I conclude the introduction here in some sense, and let me explain exactly what monotone skew-product semiflow is, and specifically what the Kamke's condition for an equation are. So a function f in Lipschitz-Carathéodory from R to n to Rn, well, R times R to n, is said to be cooperative or to satisfy Kamke's condition if it satisfies these two properties. One for each variable. Kx is for the component x that accounts for the present of the state in the differential equation, and ky is for the past, the variable that accounts for the delayed state of the problem. So Kx basically says that anytime you consider two vectors in Rn, which are ordered in the sense they are component-wise ordered, each component is smaller or equal than the one on the other, the one on the left-hand side is smaller or equal than the respective one on the right-hand side. And specifically, there's one component where they're equal, then anyways, the respective component of the vector field calculated in FTA and any other C and FTB and the same C respects this inequality. Ky says that when you get again two ordered vectors B and C and you plug them into any component of F in place of the y variable for any other vector A, you get the same inequality, the order between the components. So why are these Kamke's conditions important? Well, because they characterize what is a monotone skew-product semiflow, and so which is exactly an order preserving flow. That is, when you start from initial data phi and psi that are ordered component-wise, then the respective solution stay ordered in time when t is greater than 0. Well, of course, wherever they are defined. So Kamke conditions are the way you can try and prove if to characterize if your skew-product flow is monotone. Now, of course, monotone flows are not the most general thing, but they are very important. I mean, there's I'm just here citing two classic references, one for deterministic systems and one for random systems. There's a huge literature on monotone dynamical systems for their importance in applications. So I refer to this text for huge theory and many examples. So it's still worth a field which is very worth of attention. Okay, so the first main results says that when we have a function f that it's cooperative, that this satisfies Kamke's condition, and a little bit more, I'll be saying something in a minute, then we can find a solution, a topology that guarantees continuous dependence of the solutions and continuous continuity of the induced skew-product semiflow. Now, what is this a little bit more? I didn't want to go very much into the details given the time I have, but here there's actually two different results hidden. One of them requires a property of monotonicity on the x variable, which is a little bit stronger than kx, whereas the other one requires a property of similar to the boundedness of the L bounds, but in a very weak form because it's just for each component of the x variable. But anyways, let me just say that everything is very well explained in the paper, and I'm very happy to discuss this a little bit more. I think the takeaway message here is that if you have a monotone skew-product semiflow with a little bit of attention, then you can prove the continuity of the application. Here in particular, it says that, again, if you have L1 locally continuous on bounds, then there's also another topology, sigma p, which is a little bit weaker than tau p, that guarantees continuity as well. So let me show a bit, just to clarify how these topologies look like. Tau p is a strong topology and basically just requires the convergence of these integrals for every compact interval, the integral of the modulus of the difference pointwise, where uv is a h point in a dense and countable subset of R2n. This countable adjective here and this way of choosing the extrema are necessary to make the topology metric, which is very useful. The respective weak version of these topologies is basically the same, but now the modulus is outside. We are just requiring the convergence of the integrals themselves. So, of course, these results that I've shown for delay differential equations can be, they have an analogous form for ordinary differential equations, and this is all in the paper. Actually, in the paper, we also prove another result of continuity of the associated skew-product semiflow, where we drop the Kamke condition on the variable x when we trade it for the L1 log equicontinuity of the M-bounds. In this case, we obtain again continuous dependence of the solution and of the induced skew-product semiflow, but the involved topologies are a little bit different and a little bit more challenging in some sense. Nevertheless, I would say that this is because they require a pointwise convergence for the past variable, but a uniform convergence on compact set of continuous function as regard the present state of the problem. These topologies are one of the contribution to the theory that we make and that are essential. That's very well explained in the paper, and I don't really want to give many details here, but I am happy to discuss this afterwards with whoever might be interested. So let me say continuity of the induced skew-product semiflow is something that gives a lot of information about the dynamical system itself. In this last part of the talk, what I want to do is to show we do it in the paper, that you can actually get information, for example, on the long-term behavior of the solution just using the continuity. So I hope I was a bit clear with the explanation so far, but if you got lost somewhere till here, from now on, you can just assume that we are dealing with a monotone continuous skew-product semiflow. In any way we have obtained it through one of the previous results. Let me introduce the concept of equilibria and semi-equilibria. So a function A defined on the set of Lipschitz, on a subset of Lipschitz Carathéodory function, and image in the set of continuous function from -1, 0, or n, such that anytime we consider the solution of the differential equation with vector field f and initial data A calculated in f, the solution is defined for every positive time, is called a sub-equilibrium if basically this solution stays above the image of any time translation of f through A. And a super-equilibrium is exactly the opposite. It's a super-equilibrium when any solution stays below anytime we start in AF. It stays always below the image of any time translation of f through A. It's called an equilibrium if it coincides exactly. So in this case, this is a solution of the differential problem. This is somehow a generalization of what an equilibrium of a autonomous dynamical system is. An important feature is when these these functions are semi-continuous. A sub-equilibrium is called lower semi-continuous if anytime we have a sequence of functions in Lipschitz Carathéodory that converges to some function f, then the set of A calculated Fn is relatively compact in C. And if you consider a limit, then it stays above the value of A in the limit of Fn, which is A of f. So it's just basically the semi-continuity, lower semi-continuity, and the upper semi-continuity is the same thing, but of course the inequality is reversed. One difference here, which is anyways natural in Carathéodory, is to ask this relative compactness. Let me go on and not really get tangled with these technical details, but just remember that we are dealing with some specific functions or in the phase space that determine zones of the phase space which are relevant. So the first result is that if we have a monotone continuous skew-product semiflow obtained in any of the way of the first part of this presentation, and we have a lower semi-continuous sub-equilibrium and an upper semi-continuous super-equilibrium, so that they are ordered component-wise, then we have a way of constructing a family of lower semi-continuous sub-equilibria that specifically converge to function u, which is a lower semi-continuous equilibrium for the system. So from an original lower semi-continuous sub-equilibrium, we can construct a family that eventually gives us an equilibrium for the problem. Same thing for the super-equilibrium. We can construct a family of upper semi-continuous super-equilibria that eventually converge the function v of f, that it's a upper semi-continuous equilibrium. And specifically, they ordered in this way. So from AF and BF that we're determining a positively invariant set of the phase space, now we end up with UF and VF that determine a set of globally defined solution for the problem. Okay, this is already quite interesting, but one can say a little bit more if actually the skew-product semiflow is also a property of sublinearity. Sublinearity is just what everyone would assume anytime we consider lambda in 0, 1 and an initial data which is positive component-wise. Then the solution with initial data lambda phi is greater or equal than lambda times the solution started in phi. Specifically, a function f is said to be a point of strong sublinearity for phi if the inequalities are strict for each component whenever we consider initial data, which is in the strictly positive, the interior of the positive cone of continuous function from -1, 0 to Rn. So this is the one of probably the other main results that says that when we have a monotone and sublinear continuous skew-product semiflow, and we have that our equilibria obtained from the previous theorem are in the interior of the positive cone of the phase space, or the fiber of the phase space, then we can single out two sets in the base of the problem that have important information about the dynamical system. So E minus is constructed as those functions in Lipschitz Carathéodory, a subset. You can imagine a hull of a function, such that their alpha limit set is not empty, and in particular, it's it contains a point of strong sublinearity for the vector field, for the flow, sorry. E plus, same thing, but with the omega limit set of F. So first information is that E minus and E plus are invariant. But what's more, anytime we get a point F in E minus, then we have that U and V that in principle are just semi-continuous. Any point F in E minus is a point of continuity for U and FV. And actually more, we know that they coincide on every function F, which is in E minus. As regards E plus, on the other hand, we have that every time we consider an initial data, which is in the interior of the positive cone, then the solutions converge to either to U and V, they all converge together. With respect to this, P that's called the part metric. Don't let me go much in the details of that, but let me say that at least when you have a specific sequence converging to G, then this means that actually this convergence is uniform. So this is determining the long-term behavior of any other solution which is in the starting in the positive interior of the positive cone of the fiber. So let me conclude by saying I'm already beyond my time. That in the base